In the last video, we looked at the photoelectric effect. We were able to explain what the photoelectric effect was and able to look at Einstein's dual nature of light and how we explained it. In this last video for the dual nature of light, we're going to take a look at the other equation that we saw in that first learning target, the E equals h nu, which was introduced in the last video. We'll look at a couple of example problems for which we might want to use that. So, lecture problem number 5. We're asked to determine the energy of a photon in a red light with a frequency of 4.2 times 10 to the 14th hertz. So notice how this problem compares to the ones that we've looked at in the past, where here we're asked about energy. So that tells us we're going to use this E equals h nu equation as opposed to the C equals lambda nu, because we're asked about energy. So the relationship is just that equation. The energy of a photon is equal to h. Remember, that's Planck's constant. That's in the last video, and again, you do not need to memorize that. I'll always give that to you, times the frequency nu. So just at this point, you just need to substitute in numbers because the equation is already solved for what we're looking for. We're looking for the energy of the photon. So just plugging in our numbers, Planck's constant, the 6.626 times 10 to the negative 34th joule seconds, times the frequency of 4.2 times 10 to the 14th hertz. And we plug it into our calculator. This gives us 2.8 times 10 to the negative 19th joules. Checking our units, you might be wondering how we get joules out of that. Recall that 1 hertz is the same as 1 over seconds. So the seconds cancel, that's what gives us joules. And the joule is simply a unit of energy. You may not be very familiar with it, but it is just a unit of energy. One other point to make here, notice we're dealing with red light. We're told it's red light, so it's visible. If you have visible light, the energy of a single photon will always be something times 10 to the negative 19th joules. So something to consider, that just kind of keep in the back of your mind there to help you recognize whether or not you've done the problem correctly. If it is visible light, it will be on the magnitude of 10 to the negative 19th joules for the energy of a photon. Next problem. We are told that a photon in an electromagnetic wave has an energy of 6.50 times 10 to the negative 17th joules, and we're asked to find the frequency of the wave. So, same relationship we were looking at before, relationship between energy of the photon and its frequency. However, this time we need to solve the equation for frequency because we're asked to find the frequency. So looking at our equation, I would simply want to divide both sides by Planck's constant. That's h. Divide both sides by Planck's constant, and that gives us the energy of the photon divided by Planck's constant equals the frequency. So if we substitute in our numbers, it would look like this, 6.5 times 10 to the negative 17 joules divided by Planck's constant, which you can see there, and that will give us 9.81 times 10 to the 16th hertz. Checking our units, notice joules would cancel. Joules divided by joules cancels. That leaves us with 1 over seconds. Seconds is in the denominator, so that would be a hertz. So that's how we get hertz.